Welcome to the Duval County FSA Virtual Review for Geometry. Today, we will be looking at the test overview, brushing up on some geometry content, looking at some test-taking tips, and we'll review where to go for FSA Resources. First, an overview for the test. The test consists of two 90-minute sessions. The first is non-calculator, the second you can use a calculator. Each section is 90 minutes in length. However, students can request more time if necessary. The test is broken into three reporting categories. The first, Congruence, Similarity, Right Triangles, and Trigonometry. The second, Circles, Geometric Measurement, and Geometric Properties with Equations. And then the last, Modeling with Geometry. The test is made up of many different item types, including multiple choice, multi-select, drag and drop, and equation editor items, just to name a few. You have been experiencing these all year in your class and are probably more than familiar with them. The online calculator for the test is a Desmos calculator. This can be downloaded onto either an Android or an Apple phone. By downloading the app, you'll be able to practice with the calculator. Now, don't get excited. You don't get to bring your phone into the testing area, but you can use it as you're preparing for the test. Now for some content. Are you ready to do some problems? You might want to go now and get paper and pencil so you can work the problems with me. Feel free to stop the presentation at any time so you'll have plenty of time to work all the problems. Our first category is congruence, similarity, right triangles, and trigonometry. As a matter of fact, 46% of the test is comprised of questions in this category. Geometry has lots of vocabulary, and it's important to know the words so that you'll know how to approach the problems. In this problem, we have a right triangular prism. Notice we have right triangles at either end, and we have three separate rectangles connecting those right triangles. We are asked to determine if the segments are parallel, perpendicular, skew, or neither. So let's look at the first row. Here we have segment AB, and we also have segment BC. Notice here in the corner we have a right angle sign. That tells us that these two segments will be perpendicular. So we'll come back over here and we will mark perpendicular in our chart. In the next row, we are looking at segments EF and AC. Well, segment EF is right here, and segment AC is here. You'll notice that these are going in completely opposite directions. They're on completely different planes. They're never going to intersect. However, neither are they parallel. These two segments are what we call skew, so we will mark that they are skew. In the next row, we are looking at segments ED and EF. Here's ED, here's EF. Notice once again that they are joined by this perpendicular sign, so we know that these two segments are perpendicular. Now we are looking at segments EB and E and FC. Here is segment EB, here is segment FC. Notice that they are two sides of the bottom of our prism. Those two lines are parallel, so we would mark parallel for those. As we look at segments DE and DF, notice that they intersect right here at D. So they are intersecting segments, however, they are not perpendicular segments. So we can't mark perpendicular. We don't have a blank that just says intersecting. So for this one, we're going to have to mark neither. The last segments we will consider are segments BC and segment EF. BC and EF are at the bottom of the prism, directly opposite each other, and because they're directly opposite each other, we know that they will be parallel, and so we can mark parallel on our chart. Now, just to recap, these are the answers. Make sure that it's the same answers that you came up with. The next problem involves triangle MNP. Notice that MNP will first be translated, and then that translation will be followed by a rotation. The first thing we will need to do is to plot the points on the graph. Now, here are the coordinates of the points, and so we will need to put them on a graph. Here are the points that make up triangle MNP. However, I want you to notice in the problem, all we are asked to find are the coordinates of the final image of P. Because all we are interested in is P, we're only going to focus on P, and we're just going to kind of ignore the other 2 points for right now. As we begin our translation, notice the rule says x plus 4, y plus 8. So we will begin at our point, we will move to the right 4 places, and then we will move up 8 places. The resulting point is right here, and it is the point 310. Our new point, 310, is what we call P prime. The P prime simply means that it has been transformed one time. Now the problem says we're to rotate it 90 degrees. Well, if they don't give you a direction of rotation, it's understood that we're going to take this point and we're going to rotate it counterclockwise. Now, the way I like to rotate points is I imagine a horizontal or a vertical line leading up to this point. And so if I draw in this vertical line, I know that when I move it to the left counterclockwise, it's going to end up being a horizontal line. It's going to go out 10 places, and it's going to come up 3 places, and this will be my new point, and it's the point -10, 3. In the next problem, we have triangle CAT. And triangle CAT will be dilated by a scale factor of 1.5, centered at the point 2, 2. Dilations are the only transformation that do not result in congruent figures, unless, of course, you're dilating with a scale factor of 1. Dilations result in similar figures. In this problem, the scale factor is 1.5, which indicates that the image will be larger than the pre-image. If the scale factor had been less than 1, like 1/2 or 4/5 or 0.07, the resulting triangle would have been smaller than the pre-image. To perform a dilation, we use the distance from the point of dilation. In this problem, the point of dilation is 2, 2, and what we see is that the point 2, 2 is the very same thing as the point C. Now, if we dilate a point from itself, it doesn't move at all, and so C is actually the point C prime when we finish the dilation. Now, to find T prime, what we do is we take the distance from C to T, we multiply that distance by 1.5, and that tells us how far from that center of dilation we're moving. We're not going to figure it up exactly, we're just going to estimate that it's over off of the grid here to the left. We're going to do the very same thing to find A prime. Take the distance from C to A, multiply that distance by 1.5, and so our segment will be continued about 0.5 times farther than the original distance. And then to finish off our triangle, we'll just connect these 2 points. Then we can go back and we can label, here's our T prime, and here's our A prime. Now let's answer the question. Letter A says segment CA is congruent to segment C prime A prime. Well, segment CA is this segment that's right there. Segment C prime A prime runs along the very same line. However, it's longer. As a matter of fact, it's 1.5 times as long. And so what we notice is that segment CA is not going to be congruent to segment C prime A prime. Letter B says segment A prime T prime will overlap segment AT. Here is our segment AT. Here is our segment A prime T prime, and what you notice is that they don't overlap at all. As a matter of fact, they end up being congruent, so we know that letter B will not be true. Letter C says that segment C prime T prime will overlap segment CT. Well, here is our segment C prime T prime. Here is our segment CT, and what you notice is that they do indeed overlap. And so we will mark that letter C is true. Letter D says segment A prime C prime is parallel to segment AC. Here is our segment A prime C prime. Here is our segment AC, and you notice that these two segments will overlap. They are definitely not going to be parallel, and so we can mark that one off. Letter E says that the slope of segment AT is equal to the slope of segment A prime T prime. Now you'll remember that we looked at these very same segments a couple of minutes ago, and at that point we said no, they don't overlap, but yes, as a matter of fact, they're parallel, and so if they're parallel, we know that their slopes will indeed be equal. Letter F says that the area of the larger triangle is equal to 1.5 times the area of the smaller triangle. I know that the two triangles have a scale factor of 1.5, but what that says to me is that the ratio of the sides is 1.5. And I know that if the ratio of the sides is 1.5, then the ratio of the areas is 1.5 squared. That statement is not a true statement. In this problem, we have KLMN, which is a square, and we know that segment LN is perpendicular to segment NP. Because KLMN is a square, we know that all four sides are congruent, so we can mark that those are congruent sides. Because a square is a rectangle, we know that the two diagonals are going to be congruent, and so that tells us that LN will be congruent to MK. Now a square is also a parallelogram, and we know that in a parallelogram all of the diagonals bisect each other, and so that tells us that all four of these segments will end up being congruent. A square is a rhombus, and in any rhombus the diagonals are perpendicular. So what that tells us is that here in the center of our diagram we have perpendicular lines. There's a lot that we can tell in this diagram. Number one, looking at these triangles there in the center of our picture, we can see that using side, 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 all four of those triangles are going to be congruent. Not only are those four triangles are congruent, we can also see that all four of the triangles are isosceles triangles, and because they're isosceles triangles, we know that we can come up with some congruent angles in each one. Now we also knew this because in a rhombus, we know that each diagonal bisects two angles, and so that's enough to tell us that all 8 of these angles here around our 4 triangles are going to be congruent. And not only are they going to be congruent, we know that they're going to end up being 45 degrees. This is everything we know so far about our figure. And all of this we were able to figure out simply because KLMN is a square. However, we have one more piece of information, and that is that LN is perpendicular to NP. Notice, right here in the corner, we have a right angle. However, what you notice is on the left-hand side of that right angle, we have a 45-degree angle, which tells us that this side will need to be 45 degrees also. So this is everything we know so far about this diagram. The only thing we don't know is how long is the distance from N to P, how long is the distance from K to P. For all we know, P might be someplace way down here, or maybe P is way up here. We don't have any idea. We don't know the measure of this angle. We don't know how far it's opened up. Once again, for all we know, it might be way over here, it might be way over here. We just don't know. And we cannot assume anything. So now we can actually start working the problem. And the first statement says, triangle KPN is congruent to triangle KQN. Well, KPN was this triangle over here on the right. KQN was right next to it. And once again, we don't know anything about this distance or about this distance. And so because of that, no, we cannot say that those two. The next statement says segment PN is parallel to segment MK. PN parallel to MK. You know what I see? I see two lines, a transversal, same side interior angles that are supplementary. This statement is a true statement, and we would mark it as being true. The next statement says that the length from K to Q is the same as the length from P to N. This distance and this distance are both the same. You know, they look the same, but let me remind you, we don't have any idea where P is. It could be way down here. It could be way over there. We cannot go by looks, and so as a result, we're going to have to say, nope, this is not a true statement. The next statement says that the distance from K to P is equal to half the distance from L to N. Here's KP, here's LN. Once again, we've got that P in there. If only we knew where P was, but we don't, and so we can't mark that that's a true statement. We're going to have to say false. The next problem is a 2-column proof where we are asked to fill in the missing blanks. We start with triangle ABC. We are asked to prove that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2. In other words, we are asked to prove that this exterior angle is equal to the sum of the two remote interior angles. Now, this is a theorem that we use quite often. Anytime we're trying to find missing angles of a triangle, sometimes we use this exterior angle theorem. In our first statement, we are asked to give the reason that we know that angle 3 and angle 4 are supplementary. Well, look at where these two angles are. Angle 3 and angle 4 are right here next to each other. They form this straight line, and anytime we have angles that form a straight line, we call them a linear pair. And we have a theorem, the linear pair theorem, that says any pair of linear pair angles are supplementary. And so for this reason, our reason will be the linear pair theorem. In the second row, we are told the measure of angle 3 plus the measure of angle 4 is equal to 180. We just finished establishing that angle 3 and angle 4 are supplementary. So what does it mean to be supplementary? It means that they add up to 180. That is simply using the definition of those supplementary angles. And so the reason for this second row is simply the definition of supplementary angles. The next row, we're looking for a statement, and we are given the reason. The reason is the triangle sum theorem. Well, the triangle sum theorem simply tells us that the interior angles of a triangle add up to be 180. In this particular triangle, we have angle 1, angle 2, and angle 3, and this theorem is telling us that the sum of those three angles must equal 180. The statement we're going to fill in, the sum of the measures of angles 1, 2, and 3 equals 180. The next statement is a little bit tricky, but notice what we have already established. We know that the measure of angle 3 plus the measure of angle 4 is equal to 180. We also know that the sum of the measures of 1, 2, and 3 also equal 180. So if these angles together equal 180, I'm going to take this sum and I'm going to substitute it in for the 180 right here. That reason is the substitution property of equality, and that's going to be our reason. In row 4, I have a sum on one side and a sum on the other side of an equation, and what I notice here is that I've got the measure of angle 3 on the left, I've got the measure of angle 3 on the right. What I'm going to do is I'm just going to subtract it out on both sides of the equation. Did you hear what I said? I'm going to subtract it out. We can do this by using the subtraction property of equality. And here we have our proof. Each statement follows in a logical order from the statements preceding it. This problem has a right triangle, and we have an altitude drawn to the hypotenuse of that right triangle. Well, what that altitude does is it splits our triangle into two smaller triangles. So we have a total of 3 different sizes of triangles, and as it turns out, all 3 of them will end up being similar. Now, to demonstrate this, we're just going to make up some numbers. Right now, we don't have any idea what the measures of these angles are, but let's just pretend that this angle down here is 20 degrees. Now, looking at the very largest triangle, we have a 20-degree angle, we have a 90-degree angle. This angle over here would end up having to be 70 degrees. In the very smallest triangle, I've got a 70-degree angle, and so the other acute angle would have to be 20 degrees. And in this triangle here on the left, I have a 20-degree angle, I have a 90-degree angle, and the angle here at the top would need to be 70 degrees. Do you see that in all 3 triangles I have angle measures of 20, 70, and 90? Because of that, I know that all three triangles will end up being similar using the AA theorem. Once we know that the triangles are similar, we can set up a proportion. What I have done is I have rewritten the two smaller triangles so we can see exactly how to set up our proportion. I've placed the two triangles so that they're both facing in the same direction. The long legs are at the bottom, the short legs are on the right. And now we can see that we can pair up x is to 16 as 4 is to x. In other words, x over 16 equals 4 over x. Now to solve a proportion, we cross multiply. So we're going to multiply x times x. We're going to multiply 16 times 4. We end up with x squared equals 64. To solve this, we take the square root of each side, so x is equal to 8. And we can mark that on our chart, x equals 8. Now some of you are probably looking at that and you're thinking, well, this is really a silly way to do this. We could have simply used geometric means. As a matter of fact, with geometric means, I know that the altitude is the geometric mean of the two parts of the hypotenuse. And to set that up, I know that the x will fall at diagonals and the 16 and the 4 will be in the other two places. And so you are absolutely right. We could have used those geometric means. However, if you don't know that theorem, we can always go back and use the similar triangles. Once we know what x is, we can use that to solve for y and z. If we start on this triangle on the left, we know that the two legs are 16 and x. The hypotenuse is equal to y. Using the Pythagorean theorem, we have x squared plus 16 squared is equal to y squared. But we know that x is equal to 8, and so we can substitute in an 8. Squaring both 8 and 16, we have 64 plus 256 is equal to y squared. 64 plus 256 is equal to 320. Take the square root of both sides. Y is equal to the square root of 320. Now I can't leave the 320 under the radical, but we can break it down. Because 320 is equal to 64 times 5, I can take the square root of 64. Square root of 64 is 8. The 8 comes out, and our final answer is y equals 8 times the square root of 5. We'll use the Pythagorean theorem again to solve for z this time. And this time we're using the triangle on the right-hand side, the very smallest triangle. X is a leg, 4 is a leg, and z is the hypotenuse. As we set up our equation, we know that x squared plus 4 squared is equal to z squared. We know that x is 8, so we're going to substitute in an 8. 8 squared plus 4 squared equals z squared. 8 squared is 64, 4 squared is 16. 64 plus 16 is 80. So z is equal to the square root of 80. Once again, we can't leave the 80 underneath the radical because we can pull out a perfect square. We will rewrite 80 as 16 times 5. The square root of 16 is 4, so the 4 comes out, the 5 stays underneath. Our final answer, z is equal to 4 multiplied by the square root of 5, and we can mark that in the chart. The next category that we're looking at is circles, geometric measurement, geometric properties with equations. This category includes 38% of the test. The first problem in this category involves a quadrilateral inscribed in a circle. We are asked to find the measure of angle RSP, and we know that that angle has a measure of 4x plus 25. However, we don't have any idea what x is equal to. What we do know is that in an inscribed quadrilateral in a circle, angles opposite each other will be supplementary. So angle P and angle R are supplementary. What that tells us is 3x plus 10 added to 5x plus 10 is equal to 180. To solve the equation, we begin by combining like terms. 8x plus 20 equals 180. Subtract 20 from both sides. 8x equals 160, and divide both sides by 8, x is equal to 20. Once again, we weren't asked to solve for x, we were asked to find the measure of angle RSP. Remember that the measure of angle RSP was 4x plus 25. Now we know that x is 20, and we can plug in or substitute 20 in for x. And 4 times 20 is 80, and 80 plus 25 works out to be 105. The measure of angle RSP is equal to 105 degrees. In this problem, we have 5 points all lying on the same segment. We have a number of statements that we need to evaluate in regards to those points. The first thing we need to do is to plot each of those 5 points on a graph. Here are the points plotted on our graph, and you can see that they indeed form a straight line. If we use the slope of the line to determine the pattern, you'll notice that the pattern goes up 2 over 1, 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 up 2 over 1. And what you notice here is that there's 2 points that are not part of our problem, but we can go ahead and put them in. One point here at the point 0, 2, and the last point here at the point 3, 8. So here's our graph kind of cleaned up for you here, and you can see all of the points that we have put on the graph. Now if we look at this a little bit closely, what we notice is that there's 1, 2, 3, 4, 5, 6 parts to our graph. As a matter of fact, segment AB has been partitioned into 6 parts. We'll use those 6 parts to evaluate each of our statements. And the first statement says segment AP, and that's right here, has the same measure as segment PB, and that's right here. Now notice that AP is comprised of 3 different parts. Segment BP is also comprised of 3 different parts, and so yes, we can say this is a true statement. The next statement says the measure from A to B is half the length as the distance from A to P. Well, AB is our entire segment. AP is this smaller segment. Obviously, the larger one is not half of the smaller one. This is a false statement. Our next statement says point Q partitions segment AB into a ratio of 1 to 5. Well, here's point Q, and what you notice is that below point Q there's 1 part. Above point Q there's 1, 2, 3, 4, 5 parts. Yes, it is partitioned into a ratio of 1 to 5. That is a true statement. The next statement says point P partitions segment AB into a ratio of 2 to 1. Here is point P, and notice above point P I have 1, 2, 3 parts. Below point P I have 1, 2, 3 parts. That looks like a ratio of 3 to 3, also known as 1 to 1, not 2 to 1. This is a false statement. The next statement says the distance from R to B is equal to 1/3 the distance from A to B. R to B measures 2 parts, and you'll remember A to B measures 6 parts. Well, 2 is equal to 1/3 of 6, and so yes, that is a true statement. Now we have point P partitions segment AB into a ratio of 1 to 1. Now this sounds a lot like one that we did a couple of minutes ago. Here's point P, and remember we said above point P we have 3 parts, below point P we have 3 parts, splits it into a ratio of 3 to 3, reduces down to 1 to 1. This is a true statement. The next statement says 6 multiplied by the length from A to Q is equal to the length from A to B. A to Q is 1 part. Once again, A to B is 6 parts, and 6 times 1 gives us that 6 that we were looking for. This is a true statement. The next statement says 2 times the distance from B to R is equal to the distance from P to Q. Looking at our chart, the distance from B to R is 2 parts. If we take those 2 parts and we multiply it by 2, is that really going to be the distance from P to Q? Well, let's look at the graph. The distance from P to Q is also 2 parts, but 2 times 2 is not going to be equal to 2. That is a false statement. This is a summary of our answers. If you missed any of those pieces, back up your recording and you can look at it again. Our last category is modeling with geometry. 16% of the test is comprised with questions involving modeling with geometry. One side of a triangle is 5 centimeters longer than twice the other side. The ray bisecting the angle formed by these 2 sides divides the opposite side into 6 centimeters and 15 centimeters. We are asked to find perimeter. First thing we're going to do is we're going to draw our triangle. We simply have a triangle, and what we know about this triangle is that one of the sides is 5 centimeters longer than twice the other. So let's call this segment X, and this segment to the right of that we're going to say is 2x plus 5. And you'll notice what we have. We have 5 more than twice the other side. Now, in addition to labeling the 2 sides, we also know that we have a ray that bisects this angle. So that tells us that these 2 angles will have the same measure. The opposite side is split into parts that are 6 and 15. Now, does it matter where we put the 6 and where we put the 15? Well, absolutely it matters. We know that 2x plus 5 is larger than x, and so we want to put the larger number on the side paired up with the 2x plus 5. Now we are asked to find the perimeter of the triangle. Because we have an angle bisector, we know that that angle bisector splits the third side into parts that are proportional to the two sides we already have. In other words, x is to 6 as 2x is to 15, and we can set up a proportion. X over 6 equals 2x plus 5. In order to solve this, we will cross multiply. We multiply x times 15. We multiply 6 times the quantity of 2x plus 5. 15 times x equals 6 times the quantity of 2x plus 5. 15x equals 12x plus 5. Subtracting 12x on both sides, we know 3x equals 30 and x equals 10. Once we know that x is 10, we can substitute 10 every place we have an x, and then when we multiply 2 times 10 and add 5, we know that this side is equal to 25. Now we can find the perimeter simply by adding together all of the sides. This third side down here has a measure of 21. To find the perimeter, we add 10 plus 25 plus 21. Perimeter will be 56. That concludes our content review. Let's take a couple of minutes and look at some tips for taking the test. In the time leading up before the test, be sure to utilize all of your school resources to help you practice math problems in areas in which you're weak. These could be tutoring sessions, they could be working with other students. Take advantage of those tutoring and support services at your school. Most importantly, practice, practice, practice. The night before the test, get a good night's sleep. At that point, you know everything in the world you need to know. Don't try to stay up late studying. It would be better for you to get a good night's sleep. In the morning, eat a well-balanced breakfast. Truly another very, very important part of your day to be eating breakfast. As you're taking the test, flag any of the problems you're unsure about and then come back to them. Work the problems that you know for sure first. Don't overthink the problems. Go with your gut. Lastly, we will review where to find some FSA resources. The state of Florida has a website completely devoted to FSA resources. You can find that at fsassessments.org. This is an extremely important site and has a wealth of information. Under the Student and Families tab, you can find reference sheets, calculator policies, and a guide to practice tests, just to name a few. Under the Practice Test tab, you can find both paper and computer practice tests. Another important tab is FSA Resources. When you click on it, it looks like this. The first link is the Equation Editor Item Tutorial. Many of the questions on the FSA will require that you use the Equation Editor. Go in, work the tutorial so you will know exactly how this works. The next link is for the Scientific Calculator. This is where you can go in, you can see the calculator, you can practice using it. Lastly, we have reference sheets, both the mathematics reference sheet and the reference sheet for the calculator policies. These are two very important items that you should be familiar with. Thank you, thank you, thank you. I hope that you will spend these last few weeks preparing so that when you go into the test, you will be confident and you will do your absolute best. Once again, thank you.